Hello everyone. Today we're going to continue our section 15.2 double integral over general region. Last Friday we talked about the first part, and now we're going to talk about the second part. Okay, let's get it started. Okay, so this is a lecture 15. Okay, so this is the second part of section 15.2. It's double integrals over general region. Yeah, this general. Okay. Okay, so this is a part of this is part of two general regions. Okay. Well, let's start with the example. Okay. Remember last time we talked about type 1 region, type 2 region. Okay. So now let's look at this problem. We say evaluate let me see, I think whoops. Evaluate this double integral. So from 0 to 1 and from x squared to 1. We have root y sine y dy then dx. Okay, so if we try to evaluate this one, okay, now here we say, well, this part you don't have to write down. You just we just put it here. Note. We say it is hard to evaluate. It is hard to evaluate this one. Say x squared to 1 root y sine y dy. Because it is hard to find the antiderivative, you can try like an integration by parts or substitution. Okay, you can try, and then it's pretty hard. Okay, I'll let you try that. And then let's look at the region of integration. The region of integration is like this. D is, say, here's the x, y, and then this is the x between 0 and 1, and a y between x squared and 1. So that's this. Now notice this is a type 1. Type 1 region. Okay. Now this one, if we draw the picture, okay, let's draw the picture. So here we draw the picture. This region. Okay. Now suppose here is 1, 1. Now you think about it, x change from 0 to 1. So that means here is the origin, here is 1, okay? Now y change from x squared to 1. So this is 1, y equal to 1. Okay, this is y equal to 1. Now x squared, y equal to x squared is a parabola. So when x equal to half, y equal to 1/4. That's about here. So we draw this parabola like this. Okay, so that's like this. So this is a D. Okay. This is a D. And this curve, of course, y equal to x squared. And then this is 1. Okay. Of course, this region we can write as a type 1 region as we did here. We can also write as a type 2 region. So x, y. Okay. Now you see y change from 0 to 1. So y change from 0 to 1. Okay, notice when we switch the order, it's not just switch dx dy and change it, y change, say x from 0 to 1, and y change from x squared to 1, and then you change it to y change from 0 to 1, x change from x squared to 1. That's not. Now if you look at it, when y change from 0 to 1, what does the x change to? You need to look at this. X start from 0. This is the x equal to 0. That's the y-axis. And then change to this curve. This curve, if you solve for x equal to root y. X equal to root y. So that means the x is a change from 0 to square root of y. So that's like this. Okay, so you think about it. If I use a different color, so you think about it, it's like, say here, x change from 0 to root y. And then here, x change from 0 to root y. It's like this. Okay, so now we say, well, this is a type 2 region. Okay, now if you write this integration, okay, use type 2 region. Okay, so here we said this double integral says 0 to 1, and then x squared to 1 root y sine y dy dx is equal to, so y change from 0 to 1, x change from 0 to root y. Now the function doesn't change. Z equal to function of x and y. Now here, there's no x inside. And now this is a dx dy now. Okay, dx dy. Now you see this time, this part, it's easy to integrate because with respect to x, root y sine y is a constant. So we say this is a, say 0 to 1, this is root y sine y, right? Now the antiderivative is the x, you put in root y and a 0, which is a root y, so dy. Now root y times the root y is a y. So here we say that's equal to 0, y sine y, dy. So we have that. Now, of course, we can use the integration by parts. So here, you can use the integration by parts. Just put it 0, 1, y, d, negative cosine y, right? So u dv. Now, this is equal to uv, y times negative cosine y. Plug in 1, 0, minus 0 to 1, v du cosine y dy, like that. And then, well, when you plug in 1, so this is equal to negative cosine 1. Plug in 0 is 0. Now here, negative, negative, positive. And then algebra cosine y is sine y, so positive sine y. Plug in 1, 0. Sine 0 equal to 0, sine 1 equal to sine 1. So this is equal to sine 1 minus cosine 1. Okay, so that's the integration. Now you see this problem, we know the given integration is use type 1 region, and then it's hard to evaluate because the first integration is hard to find the amplitude. Now if we change the order, then it's easier to integrate. Okay, so this type 1 region, type 2 region, sometimes we need to think about which one to use. Okay, the third part of this section, let me see, is the third part, or did we talk about another part? Let me see. Yeah, I think last time we only talk about part 1 is type 1 region, part 2 is type 2 region. Third part we talk about properties of double integrals. Properties of double integrals. Well, let me just list some properties, and then we you can compare with the properties of a single integral. Now this one we say double integral d, if we have f x y plus or minus gxy dA. So that means the integrand can be broken into two parts. Okay, so we said this is just equal to the double integral of f xy dA plus or minus double integral g xy dA. Okay. Okay, part B, we say D, if we have a constant times fxy dA, and then this constant can move out. Okay, well, I'm just going to list this. If you really want to look at the proof, we just use the definition limit of sum, and then you can use the property of a limit, property of a sum to prove it. Okay, part C, we say if fxy is greater than equal to gxy for all the xy in the in D, then we have this. Okay, the integration of f is greater than equal to integration of g. Okay, so this is a part C. Now part D, okay, part D is say, well, we say if D, the region of integration, can be broken into two parts. Well, if you can break it into two parts, you can break it into three parts. And D1 intersect D2 contains we say at most the boundary points at most boundary points of D1 or D2. Okay, maybe not contain the boundary points of all of them, and then some of them, or not contain boundary points at all, maybe empty set. Then we have this. Then we say the integral, a double integral of D of fxy dA can be broken up into two integrals, d1 fx1 the fxy dA and plus d2 fxy dA. Okay, so that's part D. Part E, well, this is easy. We say if the integrand is 1, so this is just equal to A of D. A of D, we say, is the area of D. Okay, well, remember when we the geometric interpretation of a double integral is the volume under the surface z equal to fxy above D. Now you see, if the surface is a horizontal plane with z equal to 1 constant, so that's a horizontal plane, and the height is 1, then the volume is just equal to the base area, just equal to area D, right? Okay. Another one is a lot of times we use it for approximation. We say if m, little m, is less than equal to fxy, less than equal to capital M. In other words, we say fxy is bounded between little m and capital M, and then xy is in the D. Then we have this. Then we say, well, if you integrate left hand side, m will move out, that's like an integrand is 1, that's just the area of D. So this is tells you the double integral is bounded if the area of D is finite. So m area of D. Okay, so that's easy to show. Okay. Well, those properties we had those properties for single integral. Okay, it's kind of you can compare that, and then the proof you can use the definition of a double integral to prove each one of them. Okay, of course, if you are interested in, you should try to prove by yourself. But the more important thing here is we're going to say how to use it. Okay. So here, first of all, let's look at one example. Example 4. Okay, we say evaluate this simple double integral. The integral is just a 1, just a just a y. And then we say where D is bounded by lines, okay, x equal to -1, okay, y equal to -1, and curves, okay, and curves of y equal to x plus 1 squared, and x equal to y minus y to the third. Well, when you first look at it, this sounds like a, you don't know what to do, and then well, of course, first of all, let's see what's the region D. Okay, so here we say solution. Let's just draw the region D. Okay, you first draw the region D, and then so now let's draw the coordinate system. Okay, so this is the y-axis, this is the x-axis. Okay, you think about x equal to y minus y to the third, and then so if you look at it, x equal to y minus y to the third, Now this is equal to y 1 minus y squared. So this is y 1 plus y times 1 minus y, right? Which means when y equal to 0, x equal to 0. When y equal to, suppose y equal to 1, x equal to 0. When y equal to negative 1, x equal to 0. So you think about it on the y-axis, okay, x has 3 zeros. Okay, 3 zeros. Well, when you think about x between 0 and 1, and then y plus 1, 1 minus 1, all positive. Okay, so here this side is a positive, so it's like, yeah, I think I'm going to draw a little bit better. Okay, you can plot this several points. Okay, so if you want, you can plot it several points. Well, it is symmetric about the origin, something like that. Well, you can, that's the between negative 1, so this is a 0, negative 1, and then this is 0, positive 1. You say, why you just draw that part? Now you think about it, well, we have x equal to negative 1. Now x equal to negative 1 is a vertical line. Whoops. I think sometimes we touch the screen, I don't know. X equal to negative 1 is about this point. So x equal to negative 1 is a vertical line. So that's this line. So this is x equal to negative 1. Now y equal to negative 1 is this line. Yeah, this is the y equal to negative 1. Yeah, I think this part probably, okay. Now, you see, y equal to x minus 1 squared is a parabola. When x equal to negative 1, y equal to 0. When x equal to 0, y equal to 1. So that means the parabola is like this. The axis symmetry is x equal to negative 1. Okay, so we say this curve is x equal to y minus y squared, y to the third. And this curve is y equal to x plus 1 squared. Okay, so that means we have, this is the region. Okay, bounded by those two lines, two curves. So that's the region. Okay, that's the region. Now, how do we integrate this? Okay, so when you look at this, maybe we need to think about it as two parts. So one part above x-axis, another part below x-axis. Okay. And then I'm going to say, well, this part, if I call it D1, and this part, I call it D2. Okay? So we say, well, we have this. We say D is equal to D1 union D2. D equal to union D2. And then we say D1, if I write as, say, type 2 region, say x, y, and y change from 0 to 1. And then x change from, okay, well, this one, if I solve for x, so x is equal to square root of y minus 1. You take a square root of both sides, subtract 1 both sides. So this is a root y minus 1 less than x less than equal to y minus y to the third. Okay? And then d2 xy. Okay, then we say again, y change from -1 to 0. And then x change from -1 to the same curve y minus y to the third. So we have that. And then, well, we use the property at part D. So we break the integral into two parts. So here, then we say the integral d y dA is equal to, so we say d1 y dA plus d2 y dA. Okay, then the first integral we say is from 0 to 1, and then from root y minus 1 to y minus y to the third, y dx dy. Remember, okay, dx dy. And then this again, this change from -1 to 0, and -1 to y minus y to the third, y, remember again, dx, then dy. You see, because the x changed from -1 to y minus y third. That's why dx first. Y changed from -1 to 0. Okay, so now we can integrate each one of them. So here you see, this is 0 to 1. Well, with respect to x, y is just like a constant. We can pull out. You pull out the antiderivative of the x. So how about we put it here? Antiderivative x, say x, then we plug in y minus y to the third, root y minus 1, then dy. Same thing here, -1 to 0, and y move out, x, plug in y minus y to the third, -1, dy. Okay, so now we say, oops, so too sensitive. Okay, so 0 to 1. Now when you plug in, you're gonna have y minus y third minus root y plus 1, and then times y. So I'm gonna multiply everything out. So it's a y squared minus y to the fourth minus y times y to the y times the square root of y is a y to 3/2, minus positive 1 times y is a y, right? dy, plus -1 to 0. And now this time we plug in y times y is a y squared, y times -y third, y to the fourth, and then minus -1 is a plus 1 times y dy. So we have that. Now, of course, this is polynomial. We integrate. So here you're going to have 1/3 y to the third minus 1/5 y to the fifth minus 2/5 y to the 5/2 plus 1/2 y squared. Plug in 1, 0. And then here is a plus 1/3 y to the third minus 1/5 y to the fifth plus 1/2 y squared. Plug in 0, -1. Okay, so this is equal to 1/3 minus 1/5 minus 2/5 plus 1/2. When you plug in 0, 0. And then when you plug in 0 is a minus, okay, 1/3, and then -1 plug in is -1, and then minus negative is a positive 1/5, and then -1 to the 5th. And then minus 1/2, okay, -1 squared is a positive 1. Okay, so now you see here we have 1/3, here is a positive 1/3 is 2/3. And at -1/5, -2/5, -1/5, -4/5. Positive half, negative half cancel. Okay, so you common denominator is 15, and 2 times 5 is 10, minus 3 times 4 is -12. So 10 minus 12 equal to -2/5. Okay, so this is the integration. Of course, the integration could be negative, okay, because the region, okay. Well, we say if the function is above xy plane, this is like the volume under the surface, z equal to y, above xy plane, and on the region D. But you notice this y on this region D, and then y value, okay, on this region D, some of them is a negative, okay, negative. So of course, you are gonna have, you can think about it, if the surface is under xy plane, you're gonna have a negative volume, okay. The volume is above the surface under xy plane, and then the integration is the negative volume. Okay, so that's let me see this section. Okay, we talk about this, and then okay. Okay, that's about the section 15.2. Okay, we talk about type 1 region, type 2 region, and then we talk about the properties. Okay, sometimes we set up an integration in, with respect to one way we describe a region. We can describe a region in type 1, type 2. Sometimes both are relatively easy, but sometimes one is harder than the other. And then even if we set up an integration, the integration with respect to one maybe is easy to integrate, with respect to other one maybe it's hard. Okay, so when we set up an integration, we need to see if it's hard to integrate. When we just try the other one, even if both we can set up, and then we can see which one is easier. And those only through practice you can master it. Okay, do not have problems, and then you're gonna feel more comfortable. Okay, so please read this section and then do the homework problems. Okay, I'll talk to you tomorrow. Okay, bye-bye.